All right, we have another episode of the Money Button documentation series where we're covering not just Money Button itself, but also the technical underpinnings of Bitcoin, things that you need to know, or at least not things that you need to know, but things that are interesting to know or useful to know about how Bitcoin works, so that you can make more advanced applications. And we realized in some of the last videos that it might not be clear to people, but we're covering advanced things just for educational purposes, but in many ways, the entire purpose of Money Button is to make it so that you don't actually need to know most of these things. So many of the things that we're explaining in these videos are basically sort of extra. They're sort of supplemental to building a Bitcoin application. You can do most of this stuff directly using Money Button. And anything that you can't currently do, we're building those types of features in over time so that eventually you don't have to know all these details to be able to build applications. But today we're going to talk about something that is actually not currently built into Money Button. If you want to do this, you have to use the library directly to do this, which is the idea of taking a Bitcoin address or private key and signing data with that private key, not signing a Bitcoin transaction, but signing other data. And there is a standard way to do this that was built into Bitcoin Core many years ago. I think it was 2011, so it's quite a long time ago at this point. That you had the ability to sign not just a Bitcoin transaction, but arbitrary data. So let me just dive into the presentation here. And as usual, guys, I'm just going to share my screen and let me know if something goes wrong because it will not be clear to me if it's broken. Okay, so the basic idea here is, we haven't talked about how to sign Bitcoin transactions yet. This is a way to sign things that aren't transactions. So things like a message that you give to someone or something like that. And in order to fully understand what this means, it's helpful to have already studied hash functions, points or on elliptic curves, private keys, public keys and addresses, and ECDSA, which we've already covered all of these things in other videos and documentation. So we'll provide links to all that stuff, and those are basically prerequisites to understanding what is a Bitcoin signed message is. And just to clarify again, what we're talking about in this video is specifically signing things that aren't transactions. So built into Bitcoin is the idea of signing a transaction, which is giving money to someone. But that's not what we're talking about. We're talking about using the same ECDSA, the same signature algorithm for signing things that aren't transactions. And this is done differently. So there are a number of differences. So we're covering this first because before we can talk about how to sign a transaction, we have to talk about a bunch of other things that will be the subject of other videos and documentation and stuff before we can talk about signing it. But we have enough background now to understand signing arbitrary data. So the application for this would be something like, first of all, you could sign a file. So this could be something like, I simply sign an image so that I auth something like, if you get the image from me, you can know that I'm the person that signed that image. You can do things like sign a message, like an email or something like that, where the recipient knows that it came from you and it couldn't have been tampered by somebody else. You could do things like sign an application. So that if you build something, you can sign it and give it to people, and they can know that it hasn't been altered, that they have the version that you created. You can do other things like, because it uses the same cryptography as Bitcoin, you can actually sign with the same address that has money in it. And so you can actually prove that you own an address. So someone could say something like, there's an address out there with, say, 1,000 Bitcoin. And someone wants you to prove that you own it because maybe you're a company and they want you to prove that you have sufficient capital to to back a loan or something like that. You could prove it by they give you a message that's just a random number and you sign that random number, and that proves only the person with the private key to that address would be able to do that. So you can prove ownership of funds, or at least can prove control of funds. So there are a number of different applications of this. So the basic algorithm here is we have two, just like we have with ECDSA, but with a couple of extra sort of pieces of sort of formatting information and stuff. So we have a signing algorithm and a verifying algorithm. And so first of all, we start with some data that we want to sign. In this case, I'm just giving the example of my data as a string. And the first thing that's different than what we learned about ECDSA is that we always prefix the data with Bitcoin signed message : new line. And this is just a part of the sort of the standard here for what it means to sign arbitrary data with a Bitcoin address or Bitcoin private key. We always prefix the data with this string here because that ensures that the same signature would never be valid for a Bitcoin transaction, because Bitcoin transactions are never signed that way. So this means that someone couldn't fool you into signing a Bitcoin transaction. So imagine someone wanted to have you prove that you owned an address that had money in it. It would be really annoying if they somehow fooled you into actually signing over your money. So you certainly wouldn't want to do that. So built into the standard is a sort of a security mechanism that makes that basically impossible, because you always prefix the data that you're signing with this string. No one can fool you into signing a Bitcoin transaction. So then you hash data with double SHA-256, and then sign it with ECDSA. And then there's one other caveat here, which is you then format the signature RS in base 64, which is not the normal way you would see a signature formatted, but it's actually very logical, because you want to have so the R and S are just big numbers that are 32 bytes. And there is a slightly irritating format built into Bitcoin called DER format, which doesn't format signatures in the easy, obvious way. So this is actually a bit of a better way to format signatures than's built into Bitcoin. It's just two numbers, 32 bytes each, formatted in base 64. I think there may be one other byte in there to indicate a recovery value, which we'll talk about in a second. And then to verify the data, you do something very corresponding. So just like ECDSA, we have signing and verifying. This is using ECDSA under the hood, but also when you receive the data, you have to prefix it with the Bitcoin signed message thing and then hash it with double SHA-256, exactly like you do in the signature verification, in the creating the signature algorithm. Then they have to give you a Bitcoin address. So the way this would work in practice is, if Alice signs a message to Bob, Alice has a private key, signs the message, and then gives the message and the signature and the public key. Or rather, in this case, it's actually not a public key, it's actually an address that Alice gives to Bob. Bob then takes the address and the message and the signature and validates it. So Bob has to have some way to know that this is the correct address. So rather than using a public key like we normally would in Bitcoin, we're using an address. So we'll talk about that in a second here. So the basic idea is you actually, from the signature, instead of having the public key, you can't run the normal ECDSA signature verification algorithm. But what you can do instead is you can actually have candidate public keys that correspond to a signature. So it turns out to be possible to derive public keys from a signature. So if somebody gives you a signature, you can know what public keys, at least something like 4 candidate public keys from the signature. And so built into this method here is they give you an address rather than a public key. So you have to derive the different candidate public keys and match them against the address. And if one of them matches, that's correct. So it's a little bit different than normal ECDSA. Presumably they did this because people in Bitcoin are so used to having addresses, not public keys. In Bitcoin, you don't normally share a public key with someone. You normally share an address. And it turns out this is actually adequate for this situation, that if someone is, if you want to prove ownership of an address or something like that, you can actually use the address itself, and you don't actually have to share the public key necessarily, because that can actually be derived. So this uses a trick to do that. And then finally, that's basically it. So you make sure that the candidate public key matches the address. And if the public key matches the address, signature matches the data in the public key, then everything's good, everything's valid, and that's it. So here's an example where I used the Bitcoin signed message class inside BSV to actually sign something. So I started with my data, and then I had a private key, I generated the address that corresponds to that, and I produced a signature, and then I ran it through the verification algorithm, and it returned true. And then as a final caveat, which is that this method does not work for signing and verifying transactions, as I mentioned earlier. It's only for signing things that aren't transactions. Signing transactions works differently. And most significantly, it does not include that Bitcoin signed message prefix, because you never want to be conned into signing something that's a Bitcoin transaction. So signing arbitrary data always works differently on purpose, because we never want to be to accidentally sign over our money. Okay, so that's it for my presentation. And as usual, I'll show some examples in my terminal. But before I do so, do you guys have any comments or questions about the video or the presentation?
No, I think it was pretty clear for me at least.
No, it's okay. Let's continue.
Okay, let me add one other comment just because I'm thinking about it as we say this. So you use an address instead of a public key. There are reasons why you might want to use a public key. So we'll talk about another idea later, which is ECIES, which is a way to encrypt data to a public key. You can't do that with an address. So this method of like sharing an address and doing things like where I sign something, it's like I'm signing it with an address. It works for signing and verifying data, but it does not work for encrypting data. So that will come up again later, and we'll see that. We'll see why that matters when we talk about ECIES.
The right address from a public key is really easy, so you could share your public key anyway. If you sign a message and you want someone to be able to verify it, you can share your public key, because that person could derive the address and then verify. So
yeah, exactly. Okay. All right. Let me go into my terminal and show some examples. Okay. So as usual, here I'm in my terminal. Now what I'm going to do is I've already required VSV here. So let me require the message class, VSV/message. This is in a different class, BSV/message. I have to go out of my way to include it because it's not something that you would, it's not strictly necessary to have like a Bitcoin application. So if you're signing and verifying transactions, you don't necessarily need this. So it's just kind of in a separate folder so that it doesn't bloat the size of your application if you don't need it. So what I'll do here is I'll make my own data. So var, as usual, var data equals this is my data, or whatever you want there. I'll make a new private key. And then I'll make the corresponding address for my private key. Now I'll just print these out just so that everybody can see that it's actually working here. There's my private key. There's my address. Address, cannot read property, toString of undefined. Why is my address? Oh, that's because I'm glad I tried to demo that there, because that's because this is actually wrong. It's toAddress. Okay. Now what I'll do is I'm going to create my data, or I already have my data. Let me create my signature. So var sig equals message dot sign, and if I remember the order of parameters here correctly, I think it's message to data and then private key, I think. Okay, now what this output here was a base 64 signature. So this will come up again when we talk about signatures. This is not the way that you always see a signature formatted, but it's used specifically in this protocol. So when you're signing arbitrary data, you always get back a base 64 signature value. So now what I can do is I'll just run it through the verification algorithm. So imagine I give this data to someone and presumably they already have my address or something like that. I then give them the signature and they can verify that it's correct. And again, I'm going to try if I remember the correct sequence of this one doesn't work. I'll try the other order. Probably this way. Okay. So I just verified it. So that's it. I mean, so it's that easy to create a, pass in some data, sign a message, and verify it using this algorithm here. So I'm going to share a different screen. I'm just going to quickly glance at the source code so people can see what's going on under the hood here. Inside my.
Just a detail that is interesting is that you never have to create buffers to work with this. It works with strings.
Yeah.
It's useful because, as you mentioned, you could use this in something that is not related to Bitcoin at all.
Yeah.
So probably you're not working with numbers or buffers or anything like that.
Yeah.
You could use strings, and it's really useful.
That's a really good point. That's true. So if you're building a normal JavaScript application, if you're like a JavaScript engineer, you may not even know what a buffer is, because buffers are basically only used if you're dealing with some kind of low-level networking protocol or something like that. So it's really, you deal with it in Bitcoin. But if you simply have an application and you want to be able to sign data with a key or something like that, it is nice that you don't have to worry about buffers, that you can just pass in strings. Okay, so then we'll just quickly look through this source code because it's just kind of interesting. We'll show some of the stuff that I was talking about. So so when I sign something, it does something called magic hash, which is it puts the prefix first, then the number of bytes for the prefix, then the length of the data, and then the data. So it does this first, and then it does double SHA-256 hash on it, and then it does ECDSA, and that's what it signs, is the result of this magic hash method. So that's what's different than signing a Bitcoin transaction. Is there's a very specific way to hash the data that's different here than is for a Bitcoin transaction.
That's the security format that you mentioned before in order to realize that you're not actually signing for your money. Yes,
exactly. So this is the part that's different. And when we talk about signing a Bitcoin transaction, we'll see that this actually is a lot more complicated in signing a Bitcoin transaction. So this is it's quite different. So yes, that's a sort of a security precaution to make sure that someone can't fool you into signing your money away.
Right.
There's this other thing here. So calc.I, this is a value that is used to recover a public key from a signature. So rather than have to guess every candidate public key, it's just a number that allows you to pick which candidate public key is correct. And let's see, I think it's simply stored. It's probably stored as just a value called I in here. And then what I want to look at that I can't quite remember now that I'm explaining this is the way that it outputs the signature. Let me find that. So at ecdsa.sig, yeah, so it does that. And then, right, so it outputs that. So if we look at the ECDSA class, which I'm going to do out of curiosity here, let's look at the calc.I method. So calc.I produces a value called I, and then that goes into, so then when we output it, we have a toCompact method. So that's on the signature class. What was it called there? Oh, different signature class. Okay, there's toCompact. So it prints out the number I, basically, inside a value first. So the compact signature is the R value and the S value, R and S, but prefixed with this other number here, which is basically I, which then you can put that into a different algorithm. When you verify the signature, and I'll try and find it here. Here on ECDSA, there's this toPublicKey method, which you need to know what I is. And then you can actually derive the public key from the signature. So here's the algorithm to do that. It's all built in here. This is also a standard. Yeah, so this is discussed here on the Bitcoin Talk forum and Stack Overflow. There's some information about what this algorithm is. But for people who want to know, it's just kind of interesting that it works this way. This is not how you would normally do signature verification. Normally someone gives you the public key directly. But the way they design this standard, you verify an address. And so that means you actually use this weird elliptic curve math to derive the public key from it, and then compare that basically to the address and then to the signature to verify the signature. Miguel, were you going to say something? I heard something over there, but
no.
Okay. So anyway, that's super technical, but it's just kind of it's worth having that in mind because that is not how you would normally do signing something or verifying something. Okay. And I suppose that's it. So that's it. That's how you can sign and verify arbitrary data with the Bitcoin private key and address. And so this is useful for lots of different applications. Anytime that it's appropriate to use the same cryptography as Bitcoin, which is basically inside any Bitcoin application, it is often the case that you want to use the same crypto because it's already there. And then you can do other things like prove ownership of an address and things like that, where you're directly connecting the other application that you have to the blockchain. So it shows up time and time again. And we'll see this. This is the type of thing that people will build into applications that use MoneyButton, and we are very likely to actually integrate this into MoneyButton itself in the future for various reasons. So that's it. We're doing this this series. You can find links to everything at moneybutton.com. We have our documentation that includes all these videos at docs.moneybutton.com. We're grouping them into a number of blog posts that are available at blog.moneybutton.com. So if you want to read all of the, or sort of watch all the videos that have to do with things like signatures and stuff like that, they're grouped into those, into sections like that. And of course, it's all on YouTube, the MoneyButton YouTube channel. And if you want to ask us questions, please join us at our Telegram group at t.me/moneybuttonhelp. And we can answer questions or help people in whatever way they want to, using MoneyButton or using this library or building your application.
Great.
So any closing thoughts, guys? I think did I describe everything at the end there?
Yeah, you did. I think we're set.
Okay.
Yes.
All right. Well, then see everybody at the next video.
Okay, great. Bye.
Bye.